Hi everyone. No, I'm not dead. Yes, I'm in college right now. So that's kind of why I haven't been doing anything for like the past week or two, because I've just been busy with moving in, just like getting used to being on grounds again, and just like doing college stuff. But yeah, today we have a Codeforces round. I've not done a rated round in almost a month, and on top of that, I haven't really been practicing at all since, just because I've been busy with, well, aforementioned said college. But that's okay because hopefully this is a fun problem set. I will say that I don't know if I'll be able to record solution videos, so I think at the end of this video I'm just gonna like briefly go over the solutions that way because I don't know if I have like a time or the space to like get a whiteboard and just like write about the solutions then. But either way, I hope you enjoy the video, and as always, if you have any suggestions or whatever, just feel free to shoot a comment down below. So yeah, this is Deltix round, summer 2021. I want to start on B, because I just, why not? It's taking a while to load. Let's open up M2. Oh, M2 is loading as well. Is my internet good? Okay. Okay, we have problem A. I'll just open them up in their own tabs over here. Never mind. Okay, we're opening up M2. Yeah, I have to like log in through here to see all the problems. All right. You would like to calculate the minimum number of swaps you would need to perform to make sure the array does not contain two neighboring items with the same parity. In one move, you can swap two neighboring items. Okay, I see. So it's basically like even, odd, even, odd, even, odd, and so on. That's the only thing that really matters. And so we want to just figure out. We could probably just do it greedy, right? Yeah. Let's just try that. This is. I'll just take everything mod 2, and then int total is equal to 0 for the x array. We have n mod 2 is equal to 0, and total does not equal, and total is equal to n over 2, else if n mod 2 is equal to 1, and total is equal to, I mean, if we have 5 things, we could either have 2 or 3, n over 2. Or, okay, I mean, it's just a decent amount of casework, honestly. N over 2 minus 1. Wait, no, n over 2 plus 1, because it's like rounded up. Yeah, and then otherwise it should be impossible. Okay, so let's just go through all of these cases. I need to, okay, so for this case, I need to try both 0, 1, and 1, 0. So int res is equal to, I mean, I guess it could be a long, so I'll just static final long infinity is equal to long dot max value over 2. Okay. Or I guess we just start from 0, whatever, it's fine. Alright, int 1 count is equal to total, yeah. And so for int I is equal to 0, I is less than n, I plus plus. We just want to count the inversions of. Yeah, I guess if we focus on just moving the ones in their right location, then it should just fix itself. Or maybe it's like, Wait, it's 2 neighboring, right? Yeah, okay, good. Okay, what's like a quick way we can do this then? If it's like 1 0 1 0 1 0. I mean, if it's like 1 0 1 0 1 0, I could probably just like count the number of inversions that way. I mean, it might just be easier to do. Yeah, I don't know. There has to be a better way to do it, but I'm very rusty right now because I haven't done CP in a few weeks. So whatever. Look, this is the best way that I can think of doing it. It's whatever. Okay, so we need to assign like values, I guess. One tag is equal to. Okay, wait. So it's like I want to do 1 0 1 0 1 0. So we start from 1 2 3 4. We add this, okay, and then we just do I should use array list. Yeah. All right, p0 is equal to 0, p1 is equal to 0, 4 and 5 is equal to 0, I is a set of is plus. Okay, so if array at I is equal to 0, then, or wait, it's like, yeah, we wanted to assign like the 0 first. Yeah, we want to do like 1 0 1 0 1 0. Okay, so it's like if I mod 2 is equal to 0, then lol at I is just going to be equal to, oh, okay, no, it's at that location, so it's like ones dot get. Wait, no, if it's equal to 0, zeros dot get. Yeah, zeros dot get at p0. This is a location, and this is just equal to else. We do the same thing except it's long ones dot get. This isn't just a temporary variable. Start at 1. Long res is equal to inversions of this array. P0 is equal to P1, which is equal. I'm doing this in a very like stupid way, but it's whatever. Okay. So we start over here, and so this means that we go with the zeros first. We can do this to just reverse the parity, and then inversion. All right. Static long inversions of an array. Where n plus 3. N is just the length of the array. E. No. Res bit.find from. I want to find all values that are. Okay, it's added before. It says all values that are higher than it, so it's just. X to n, the maximum value should be n, and then bit.add x1. Okay. Otherwise, we start on. Okay, if total is equal to n over 2, we have to start on 0. So it's pretty much just this logic over here. 0, 1, 2, 3, 4. Yeah. Otherwise, if it's over here, then we have to start on the 1s. So it's basically just this over here. Int p1 is equal to 0, is equal to 1. Long res is equal to inversions of this array. Alright, let's see if this works. 1, 0, 3, negative 1, 2. Alright. It seems to be a working, like, piece of code. Yeah, let's just try it. I'll look at problem A right now. How's the Q, first of all? Okay, we got it B. Time limit? Seems fine. Alright, problem A. You have two numbers A and B initially both equal to 0. You want to do 3 different types of operations with them quickly. Before each operation, some integer k is picked, which is then used to perform one of the 3. We can either add k to both A and B, add k to A and subtract k from B, or add number k to B and subtract k from A. Okay. And numbers can become negative. We want to find out the minimum number of operations you would have to perform to make A equal to its favorite number B and make this equal to second number D. And sometimes it's not possible. Okay, well, if we add 2 numbers by an even number, then it's whatever. Like, we can't do anything. Yeah, because the parity always changes the same way. So if the parity of A and B don't match initially, then it's impossible. Oh wait, A and B are initially something else, right? Oh, they're both initially equal to 0. Oh, I see. I mean, the parity thing, it's like, if they just have different parity at the beginning, then it's never possible. So that's like something we should note. Right, we have this, we have, oh wait, I guess this is x and y, and we start A and B as both 0. So if x mod 2 is not equal to y mod 2, then it's impossible. Otherwise, I believe it's always possible. And the way we can do this is, well, if we add a number k and then this, they can either both become the same number or they change by an even amount. Yeah, that's like, if they're the same number, else if x is equal to y, then if x is equal to 0, then it's obviously, we don't need to do any moves, otherwise we can just do one move. And then last move is like, we can always do into, because we can use one move to like establish a difference and then use the second move to shift everything up. Alright, okay, we got A. I'm going to move on to C. I'm going to just read it here. You have a favorite bracket sequence. Since its favorite number is quite big, he provided you with a sequence of positive integers C, where Ci is a number of consecutive brackets. If I is an odd number, and this is an even number. Example for bracket sequence is 3, 2, 1. Oh, okay. The total number of contiguous subsequences of original bracket, which are regular bracket sequences. N is only 1,000. Huh. But Ci is very big. And, okay, it always fits in long. Oh yeah, C is the same difficulty as D. So, maybe I should read D as well. Hey, D is interactive. You have a certain sequence of integers due to security issues don't want to reveal to the completely. Result of the bitwise and of two items with indices list and the bitwise OR. I want to find the kth smallest number. Oh, we probably use binary search or something, right? Maybe. I don't know. Okay, I want to think about C a little bit more then. I want to open up from here. Alright, so maybe we think of it as every subarray, and then for each subarray, we want to figure out how many possible bracket sequences. Okay, so like if we have like some subarray and we add a new subarray, we can only add at most one more bracket sequence to our answer. That is not true. I just realized it's not true. But, I mean, if we fix a left boundary, it says that there's too many left boundaries to consider. Like maybe we could do something where it's like, we look at the left, we fix left and right endpoints for every like regular sequence, and then we figure out like how many bracket sequences fall under like this category. Or like the middle ones, they have to count no matter what, and then these like they just do some casework. Yeah, that sounds like it'd be correct. Yeah, I'm gonna try that. So it's just okay. So we do this for obviously for left endpoints we only want to consider opening bracket sequences. So if left is equal to 0, left is less than n. And right is equal to left plus 1, right is less than n. And then same thing over here. And then over here we have to like update the middle, I guess. I'll just call it middle. And then at the end it's just like middle minus equal to array at right. And then middle plus equal to array at right plus 1. Right, because then it's like this and then this and then it moves on here. Yep. Okay, so how do we do this part then? If we have okay, so basically we know that in this particular scenario, if we fix some part in the left, there's exactly one in the right. Maybe this is something we can binary search. Yeah, I want to try binary searching for this. So in other words, we could do something like, okay, well, what is the complexity of this? I'm only checking every 2, so it's 500. It's like roughly 500 times 500 if I do binary search on 10 to the 9 is 30 operations. That's probably fine. Yeah, I mean, it's a 1 second time limit, but it's a pretty good constant factor. Let's see. So, int. We want to get the minimum number. Okay, well, hold on. Let's say if we, we want to choose a minimum number of opening bracket sequences we can have. Like the minimum number of opening bracket sequences. So, in other words, you need to do something like this. Oh, wait, this isn't correct. Yeah, wait, because these aren't bracket sequences. How, there's like, There's no like really good way to do that. Actually, it might not be that hard to handle because we have this middle section. Obviously, we want the whole sum to be 0, but we just need to make sure that this middle section, whatever like the smallest like minimum like that it dips in, we want to have at least like that many brackets to here. Okay, so it's like long min is equal to 0L. Yeah, and so then min is equal to min of itself in the middle. Yeah, and that's just something we have to handle like this. I think that it's probably okay. Yeah. And so if array at left, it has to be at least as large as min. Otherwise it's just straight up not possible. If over here it's at least as large as min, then it's possible to upset this over here. But if it's at least as large as min, then we would have to have 1 based on like this right sequence over here as well. In which case it would have to be strictly greater than. We'd have to have like as we at least min plus 1, so it has to be strictly greater than min, in order for it to be like possible at all. On top of that, it's also like we also need to make sure that even after using min, I mean we could just use 1 bracket sequence in here. Yeah, that's fine. Yeah, we just use min number of opening brackets. Yeah. Alright, so we obviously need at least 1, and we can use at most array at left. Let me just do that instead. So this is how many we have. So so long as mid is at least as large as min plus 1. Wait. Yeah, if min is at least as large as min plus 1, and it also has to be like less than something. And min is less than or equal to min plus array at right. I mean, as long as we minimize min, that should be okay, right? Because we know it's always possible to do it in like 1 bracket sequence as long as we take care of the middle part. So if it's like, if you use this many bracket sequences, we need at least X many bracket sequences. Yeah, so it's like some range of values that you can choose in here. If we have too few bracket sequences, then okay, I'm just gonna maybe I just binary search on 2 boundaries, maybe? Like for example, if we know that the minimum number of opening bracket sequences is that many plus 1. I want to choose the maximum number. So if mid, we just need to make sure that min plus 1. Okay, wait. Let me int min open is equal to min plus 1, or I guess long max open is equal to shoot. Yeah, we just need to make sure that min, which is like number of like decreasing in here, plus the total number in here. And then it's just the min of array at left, and then whatever this value is. Max open minus min open plus 1. Let's try this. Nope, unfortunate. Let's try. Let's see, what is it off by? Oh wait, hold on. Oh, that's right, this one is less than n. Let me do this. Yeah, okay. 9, okay, so I'm over counting a little bit. Yeah, I'm just over counting. Okay, 0, 4. So subsequence from a 3rd to a 10th character. From a 4th to the 10th, from a 4th to the 9th. Okay, so there should be 3 in here. It's only 3. So if we have like 4 and 1, that should be counted as 1, right? Let me try this. If we do left plus right plus min open, max open. Maybe this. 1, 1, 1. Oh yeah, 0, 1, 1, 1. Yeah, because there's, yeah, we can have at most 1 and at most 1. If it's 0, then 3. Wait, 0 to 3. So like if it's one of the 4th to the 9th character. Okay, so there's 3 ways of doing this. Oh wait, no, it's just, oh, we can't have min open has to be at, oh wait, I'm stupid. Okay, I'm being very stupid. It's -1 times min plus 1. Yeah. -1. Okay, hold on. That's a little better. If it's at least as big as this. Yeah. That makes a lot more sense. Okay, something's wrong though. Min, oh, it's probably, yeah, -1 times min. Yeah. Yeah, because min is negative. Like, I was thinking of it as a positive, like, number. Okay, 0, 1, there's one way of doing it. That's, okay, so from 0 to 3, if there's a point from here and a point in here, there's only 2 ways to do it, so I'm saying there's 3. Wait, so I'm saying I need to take at least 2 minimum opening brackets and those 4? Wait a minute. 3rd to the 4th, so I take 2, I take... Okay, so it's like from the 3rd to the 10th character, from here to here. Yes, it's like I have something that closes off like this. Like right here? Yeah, right there. Wait, so if it's 0, 3, 2, 4, if we have an element, like, for example, how? That hurt. Okay, so I'm saying that it's possible to have 2 opening bracket sequences, which it is, but it's also possible to have 1 opening bracket sequence. Yeah, because we can have something over here and then something close off over here. And the way it's represented is, I have -1. Yeah, so min becomes -1, and then I add on 1. So like the delta in here is 1, but, oh, I'm not accounting for the delta. Okay. So this is the minimum number of opening brackets that we need, I think. Yeah, I mean, that's a lower bound. And then we can only, and the maximum number is negative, no, it's currently min, yeah. It's a current min, not -1 times min, it's just -1 times middle, I think. That makes a little more sense. That, let's see. Nope. Okay. If we have a value in here, the value extends off from, like, up there. 1, 2, 2. But 1 is possible. Like, 1 should be possible. Like, having a 1 bracket, right? Oh, it's based off a middle. Okay, so we need to have at least this many, right? But if middle is equal to 0, then min open decreases by 1. Or if middle is I mean, we have to have at least 1 in there anyway. Yeah, okay, if it's like min open, we just need this many, and then it's just that many left. Nope. Okay, hold on. Let me think of this more carefully. So we have this middle part. We have min. We also have like a total delta. This is equal to middle. We have like some number of opening brackets, some number of closing brackets. The minimum number of opening brackets we can have is based on what the total delta of this middle segment is, as well, the minimum like depth of the segment, I guess. Yeah. So it's min. So we need, if it goes down to min, then we need at least -1 times min plus 1 brackets. Yeah, because we need to offset all of his middle brackets and have at least 1 more bracket to append to this right part. So we have this, the minimum that we need open. The maximum that we can have open is based on the middle, like this middle portion, plus, like the middle portion, like whatever the delta of this middle portion is, if like a positive delta, for example, then, okay, long max of, okay, so if middle is greater than or equal to 0, then that means that we have a lot of like opening bracket sequences. So we have, the maximum number we can have is basically for a value in here. If we have this many open, then it depends on how many in here. I mean, I'm just going to binary search for long max open. Yeah, if it's 1L, long high is equal to array at left, while low is not equal to high. Yeah, basically, int mid is equal to low plus high over this, or long mid. And then if this is the number of like opening bracket sequences, if the number of opening bracket sequences that we have plus the middle part is strictly greater than the number of closing brackets in here, then we have too many. So mid is equal to high minus 1. Otherwise, mid could potentially be higher. And then the maximum open open should just equal to low. And then I'll only add it on if min open is less than or equal to max open. Low plus high, mid, oh, low is equal to mid. Wait, hold on. If mid is too high, so high is equal to mid minus 1, otherwise low is equal to mid. There we go. Really? It's still not working. Why? Okay, one bracket sequence is always possible though. 0, 1, 1. No, but 1 is possible. Like having one bracket up here is possible. Oh, okay. It's like minimum open. Yeah, it's because of this part over here. Yeah, once we offset min, just because we offset min doesn't mean we offset. Yeah, okay, wait. After offsetting min, if middle is strictly greater than 0, then we can afford to take one away. Yeah, it's like +1, min open minus minus. Oh my god. What? Bruh. This should not. How is this hard? It's not even that hard. I'm just trolling. Okay, what's happening here? 0, 1, 1, 1. Wait, so what does this even look like? It's 1, 2, 3. It's 6. Total sum is 10. We have, wait, no, it's 8. Yeah, it's 8. If we have something like, okay, so you're saying from 0 to 1, there's one way to do it. Yeah. From 2 to 3. Wait. But I could do like 0, 1, 0, 1. I could, like, middle could be equal to this, but that doesn't mean that. Let me try this. If this is at least as large as min open. Okay, this is still 5. Is this still 6? Yeah. It's just that this is now giving 6. Oh, this is so annoying. Which one did we not include? Maybe, did we not include the entire bracket sequence, maybe? Like, if I just had 2 and it was 1 or 1. No, it's included. I'm gonna spend like a few more minutes, and if I'm still stuck, I'm gonna move on to D. Yeah, okay, if it's indexed from 0 to 1, if it's indexed from 0 to 1, wait, what about 0 to 3? Why isn't that registering? 0 to 3 is like, I mean, for minimum delta is equal to 0. Yeah, that means we just need at least one bracket sequence. Oh, is it middle greater than or equal to? No, that's too much. No. Yeah, it's not. It's just, okay, because we need to have one bracket sequence in here no matter what. If you have one bracket sequence, the maximum number of, I'm just going to binary search for this as well. Screw it. Here to stay. We want to binary search for the minimum number of brackets that we need. Long mid is equal to array at left plus array at, no, low plus high over 2. Alright, well, if this is strictly less than -1 times min, then we continue. Otherwise it's always possible, question mark. We just need at least this many. Long min open, in this case, would now just be low. So if if mid plus the middle we just need to make sure this is at least this is greater than 0. Wait, we want to find the minimum value. The minimum number of bracket sequences. If mid plus middle minus 1 is greater than or equal to 0, then wait, does this take into account array at right? Yeah, I guess over here. Then we want to, okay, if we can support this number, then I is equal to mid, else low is equal to mid plus 1. Okay, that gives 7. This gives 6. All right, let's see. Okay, we got C, finally. That took way too long, but, okay, problem D. I already read problem D. It's interactive. How big is n? It's almost 10 to the 4. Are all numbers distinct? Distinct. Pairwise distinct? Okay, maybe not. Oh, okay. It doesn't have to be. What is the result of the bitwise AND of 2 items? Okay, so we can query the bitwise AND. Bitwise or and you'll get an integer x, not including a finish operation. Bitwise and or the bitwise or. Okay, if we know the bitwise and, okay, bitwise and tells us which bits are set in both numbers. Bitwise or tells us which bits are not set in both numbers. So, and then everything else is just up in the air. I can close that. I already solved that. I'll open up E and F. Okay, E seems, okay, E, and this is F. F seems like bitmass stuff, probably. Okay, so problem D is if it's something like bitwise or bitwise and tells us the bits in here. We want to find the kth smallest number in the sequence. Okay, if two numbers have a bitwise and equal to each other, and they have a bitwise or also equal to each other, that means that these set of bits are not set, while these set of bits are set. But it's possible if, I mean, it could be hard to tell though, even if it's like 3 and like 3. Oh, but bitwise or would tell us. Yeah, if bitwise or, okay, if bitwise and of two numbers, we know it's x. In other words, if a and b is equal to a or b, does that imply a is equal to b? So if we look at one bit, so if, I mean, obviously it works if both bits are set, but if we do 1 and 0, then this bit will give 0 and this bit will give 1. Yes. Okay, that does imply it's equal. Okay. So when we query two numbers, I think this means we can always take what does this mean? What does this mean? What does this mean? Okay, what if, okay, let's just say we want to find the minimum number where k is equal to 1. If k was equal to 1, then querying the and will tell us, if we query the and the or of like two numbers at once, then we can figure out, okay, so obviously if they're equal, then they're equal. If the bitwise and, then like there has to be some bit that's like first. Oh, we know where it is, we just don't know what this best number is. Right? Because we know one, yeah, because both of these operations, they don't preserve order of the bits. All they do is that they can just tell us what the largest bit that is different by is. But that's not very helpful. Okay, that's not very helpful. What do we do then? If it's a or, bitwise or of two item indices. Okay, so in here, okay, and the 1 bits are important. In here, the 0 bits are important. Because that means for like these numbers, we know, like, for example, we know that this would be 1, this would be 1, we know this would be 0, and like this would be 0. We just don't know what these bits are. We just know that 1 is 0, one of them is 0, one of them is 1. How can we figure out that information? I mean, if all of the bits that we choose, if we query like these two numbers, for example, and we get like or is all 1s, that doesn't help us at all. I guess it does help us in that we know that one of these is 0 and one of these is 1, and like it's just arranged like that. But I feel like that's not the best way to do this. Cause yeah, that doesn't tell us that much. Okay. Bitwise and then bitwise or. If we want to find the smallest value, then it was 2 times n queried. Well, 2 times n, if n was equal to 3, there would be, we could use at most 6 queries to figure out which one of these is. Oh wait, do we print the index or the actual value? K smallest number. Okay, we print the actual value. So we have to determine what the actual value is. Yeah, that's kind of difficult. Do we do like some divide and conquer stuff? I mean, that's ceiling of log. No, that's ceiling. Yeah. Maybe binary search? No, but like that's too many queries anyway. Yeah, too many queries. If we choose a, how many queries? What if we just choose a random index I, and then we figure out what is its number in its respective order. So we have like this index. If we compare it to the number like next to it, for example, we know that some bits, like we know what the matching bits are, like, and we can get that in 2 queries, but we don't know what the unmatching bits are. Yeah, so if everything is 3, I mean, I guess if it's equal, then you could just say it's equal. But what if it was like 2? What if our only numbers were like 2, 1, and 3? I learned any other restrictions that I'm not picking up. Guarantee it's almost 10 to 9. Okay. Okay, so if we AND these, it's equal to 0. If we OR them, it's equal to 3. AND is equal to 0, OR is equal to 3. Okay? AND is equal to 0, OR is equal to 3. If we check these pair of numbers, then it's like 1 and then 3. Or I guess, 1 and 3, we know that 1 is a fixed bit in both of these numbers, or like 2 to the power of 0, and then this is ambiguous. And then over here, 2 and 3, we know that this is a fixed bit, and we know that the mask of these is this. Bitwise and bitwise OR. Okay. Let me just open up these problems, just in case. Okay, I'll read E. You have 2 arrays A and B, consisting of n items for each segment, or for some segment. You want to know it's possible to equalize the values using a balancing operation. The values are equalized if for each I from L to R, they're equal. Okay. To form a balancing operation, an even number of indices must be selected so that this is this. Next to items, array A get incremented by 1 items. Array B at positions this get incremented by 1. even number of indices must be selected such that this. The items array A at the odd positions, or like the odd positions of a chosen subsequence, increase by 1, and these get increased by 1. Okay. I want to find out if it's possible to equalize the value of elements into 2 arrays for each segment using some number of balancing operations. Oh, and the minimum number. And you just query 2 segments, and if it's impossible, you specify. We get increased by 1, we get them decreased by 1. Maybe it's just like, if we take like every under index, we can just like shift it or something. Maybe. Okay, I want to think about, yeah, D doesn't seem that hard. No. Maybe I just need to think about it a little bit more. So if we have like, or okay, I get the bitwise OR of 2 numbers like this, and I can get the bitwise OR of any subarray. Right? If you get the bitwise OR of any subarray, then versus a bitwise AND. So like starting from here, we know that the bitwise OR prefix just tells us which bits have not been set at all yet. Yeah, but it's possible like numbers later have that like bit like not set, and then it's impossible to get information based on that. Yeah, and especially if like over here it's like that bit was set as 0, then like it's whatever. What if we query just a bitwise AND between everything first? Okay, like for example, if we query the bitwise AND of all adjacent numbers or something, then if we have bitwise AND of A and B, bitwise AND of B or C, B and C. Yeah, so it's like A and B, and like B and C. I'll let this equal to X, let this equal to Y. If they're different, then, okay, well, if they're the same, then that doesn't really tell us much. But if they're different, then this tells us that if, for example, X was less than Y, X being less than Y would tell us Y, like, both B and C are greater than A. Yeah, both B and C are greater than A. Oh wait, the bitwise OR and bitwise AND of... Wait, okay, if the bitwise AND of A and B is equal to bitwise AND of B and C, and the bitwise OR of A and B is equal to bitwise OR of B and C, does that imply A is equal to C? I feel like the answer to that is probably no. Okay, let's say like this is B, for example. If A was, say, like equal to Right, b is equal to, so let's just say, for example, a is equal to 0, 1, 1, 0. Then our and would just be equal to 0, 0, 1, 0, and our or would just be 1, 1, 1, 1. If you have some fixed b, we know that if we just create any c whatsoever, it has to have this bit set. And then it may or may not have. Okay, well, you know that because or is equal to this, c's bit has to be this. And then because and is equal to this, then we know that like 0 and 1, like if this is 0, if bitwise and is equal to 0 over here and this is equal to 1, that means this has to be 0. This has to be 1, this has to be 0. Wait, maybe it is. Yeah, we can determine if they're equal to each other, then they're just the same number. Yeah, so given, like, if we know these quantities and we know the quantity of b, then we can know the quantity of a. And we know that if a and b is equal to b and c, then like that implies b is equal to that. So if we query all of those, and then afterwards we say, how do we find the kth largest number though? The result of operations for numbers you have selected. If we want to figure out the minimum, then I guess after we establish something, we get like an order, and then we know where the index of that value is, and then we can, if we know where the index of like the kth value is, maybe we can figure out these values based on this. Like for example, if we did something like A and B, B and C, if we have some, wait, A and B, B and C, A and B, B and C, if we have, okay, this is equal to X, this is equal to Y, but what is B equal to? And we know some of the bits, we don't know all of them. And what if they're all equal to each other? Then that's just weird. Yeah, that would just be really weird if they were just all equal to each other. Bitwise, is this similar to what? I feel like this is similar to a problem I've seen before. Okay, just like bit masks and then interactive. Where have I seen a problem like this before? It's not this, I don't think. Yeah, because like for this version you can just like ask. Yeah. Bitwise and bitwise or. Wait, so 2 bits are set only when, or like it shows that the bit is set when both of them are in here. But or, okay, so we know that in this case. Can we figure out all the bits in like this number? Because we know the bitwise OR. Okay, we get like just 2 adjacent numbers. If the bitwise OR of this number is equal to that, and then the bitwise OR of this number is equal to this, then okay, so let's just say like if the bits set in here are 0, 0, 0, then the ORs would just tell us it's all 0, and like that's easy. 1, 1, 1 would just tell us bitwise and is both 1. Yeah, because we know the bits are both contained here and here. That's easy. What if it was like 1, 0, 0? Then the bitwise and in here would tell us here, bitwise and in here would tell us in here. Or like bitwise OR would also tell us that as well. So the bitwise OR would tell us like this bit doesn't exist here. I mean, if and is all 0. If the and was, okay, if and was 1 in one of these and 0 in here, then we know B has to contain this bit, and C doesn't contain that bit. Okay. So, that's interesting. So, like, in other words, for all values that are like this and this, using A and B and A or B, we can essentially just sort these indices by like certain values, and then once they're sorted, we just like figure out which index it is and then use that information of adjacent indices to find out the actual value. Okay, I want to try this. So we're given n and then k. Yeah. We're given n then k, and then we ask our questions. Okay. I don't have to read an array at all. No. Public static void query. Int a. String message a b. Buffer created in file. Where's get? Okay. Int. Okay. So we have this. We want to first query all the adjacent. So, and. Do you want to query up to n and n? Wait, n plus 1. I want to do from 1 to 2. So it's like for int I is equal to 1, I is less than n, I plus plus. And that I is equal to, we want to query and I plus 1. Or that I is equal to query at or I plus 1. Can we figure out the and in the or query given like 2 other numbers maybe? Like how do we, like does this allow us to check the and and the or of all between any pair of numbers, or no? So So you have if A and B is equal to X, A or B is equal to Y. If we have, I mean, just like any number in general, I guess. Yeah, A, if and C is equal to, like, Q, A or C is equal to R. So if we have, like, what is B and C equal to then? Well, we know which bits are both set. Okay, well, we can find A uniquely. Yeah, this is enough information to tell us the value of A itself. And if we know the value of A, then we know the value of B. Right? Or is that not right? A and B, A or B is not enough information. But if we have A or B, A or C. Right? Because if a bit is equal to, let me just make sure I'm not being stupid. Okay. If the and, okay, so for each bit, I guess, let's just say if it was 0, 0, 0, then our ands, okay, then our two ands would be 0, 0, our ors would be 0, 0. If it was 0, 0, 1, our two ands would be 0, 0, and our two ors would be 0, 1. If we had something like 0, 1, 0, our two ands would be 0, 0, our two ors would be 1 and 1. If we had 1, 0, 0, it would be 0, 0, 1, 0. If we had something like 1, 0, 1, it would be 0, 0, 1, 1, 0, 0, 1, 1. Yeah, this is a problem. But is that the only problem? Because if that's the only, like, problematic thing, it might still be possible to use this fact. Like, if we have 1, 1, we have like 1, 1, 0, then it's like just 1, 0, 1, 1, 0, 1, 1, and obviously 1, 1, 1 is just all ones. This is 0, 1, 1, 1. Okay, so the only problematic things are this and this. Those are the only problematic, like, occurrences. Can we, and how, is there a way we can remedy this? That's like if this is a common element. Okay, well, if that's a common element, then we can just use another query, maybe? Wait, are we sure that this is, okay, if it's or is 1 and 1, the or in here is 1 and 1. Yeah, and the ands are obviously this. So either B is greater than both of them, or A is like, A and C both have this bit. Oh, and we can figure that out by using A and C. Yeah, because 3 times 2 over 2. Okay. That's better. That's a lot better. Get first 3 numbers. For instance, I is equal to 4, I is equal to n, I plus plus. And then finish plus array at k. Get first 3 numbers a, b, c. Okay, so int ac and is equal. Okay, well, and wait, what? Okay, I'll do it x, y, z. Yeah, x, y and is equal to query and 1, 2 in file, and x, z and is equal to query 1, 3. Wait, n is always 3, right? Or at least 3, yeah. everything except for or now. XY, or, okay. So 4 and bit is equal to, I mean, it's almost 10 to the 9, so 29 maybe? Yeah, if we have a value that's like, okay, well we have int a is equal to min of 1 and yeah, let's take the first bit. So we just want to compare like AB, AC, yeah, this is like A and B, B and C versus A or B, A or C. Yeah, and so it's just like A and, so like X and Y. So it's like X, Y, and 1, let's just say, yeah, like this bit in 1. B is equal to, yeah, this X, Y, and it's the same thing over here, except we just use min YZ and 1, let's just 1. And C is equal to, I mean, we're just checking the bit to see if it's like good or not, right? X, Y, or. And then D is equal to the same thing, except it's just YZ or. Yeah, that works. And so, if A plus B plus C plus D is equal to 0. Okay, well, and mask is equal to, it's just D plus 2 times C plus 4 times B plus 8 times A. If mask is equal to 0, then it's whatever, like, yeah. Else if mask is equal to, okay, if mask is equal to 1, then we do, okay, so this case is handled. If it's this case, then we know that C has a value, or like, I guess, array of 3. Yeah. Else if mask is equal to, this is a special case. If mask is equal to, yeah, if mask, this is if mask is equal to 1. This is if mask is equal to 2. Then we know that A has a special value. So like array at 1, or like has not a special value, but the bit set. Mask is equal to 3. Yeah, mask equal to 3 is a special case. Mask equal to here, maybe. If it's like 1, 0, 1, 1, that's, what is that? 11? That's 11, 15 minus 4 is 11, yeah. So if mask is equal to 11, then we know that the array of 1 and array of 2 have this bit. So array of 1 has this bit, and array of 2 also has this bit. So we have this, and then if it's mask is equal to 7, because then it's like 4 plus 2 plus 1, then we know that array at 2 and array at 3 have this bit. So array at 2 and 3. So we have this, we have this, we have this. Okay, so which masks have we considered? We've obviously, okay, we have 0. We have 1, we have 2, we have, oh wait, no, not, wait, mask is equal to 2, where is that? Oh, right here. Okay, 3, we just skipped one out, 11 in here. Oh, and then else if mask is equal to 15. Then all three of them get set. Else, okay, let's first assume by default array at 2 has a bit, and then if xz and one left a bit, if this is greater than 0, then array at 1 gets this bit, and array at 3 gets this bit. Otherwise, only array at 2 can get this bit. True. All the values are most this. Okay. Array 0 is equal to -1. So if we have all of these, then int and is equal to query. Okay, if we know this value, then we know what that value has to be. Yeah. So then we just query and like 1 and then 3. Or I guess just 1 and then I. And 4 is equal to 1 I in file. 4 and bit is equal to 29. If bit is at most 29, then we know that. Well, okay, so if okay, so the bitwise and of both of these in numbers, oh wait, no, if array at 1 and 1 left of set b is greater than 0, else. If okay, so if this value is greater than 0, then if and 1 left at b is greater than 0, then we know that array at I needs to get this bit. Else, and then if the or, then we do this. Yeah, and then we sort array, and then we just print k. I'm just going to submit this and see what happens, because it's interactive. I don't want to like. Okay, that's fine. Wrong answer to number is guessed wrong. Output. Okay, let me just run it on here then. An example of hidden sequence is this. Okay. So we provide 7 and 6. The answer should be 5. If we give and 1 and 2, bitwise and of 1 and 2 is 0. Yeah. Bitwise and of 1 and 3 is 0. Bitwise and of 2 and 3 is 4. Bitwise OR of 1 and 2 is equal to, I believe that's 7. Bitwise OR of 1 and 3 is 5. Bitwise OR of 2 and 3 is just 6. Array at 1 plus array at 2. Array at 3. Okay, so it's 004756. 0, 0, 0, 4, 7, 5, 6. Okay. 0, 0, 4, 7, 5, 6. 1, 2, 4. That's not right. Oh no. Wait, hold on. 1, 4, and 6. What is the case in which it's 0, 1, 1? It's when the sum is equal to 7, right? Like a mask is equal to 7. Okay, what if I just do, because I know these values aren't very big, right? It's the biggest bit that we care about is power of 2. One left is that bit. Okay, all of them are one left is that bit. Okay, good. 7, 6. We have 0, 0, 4, 7, 5, 6. We have 1, 2. There's no way that's right. Wait, hold on. Bitwise order of 1 and 6 is, that means, okay, so this is what 6 is in bitwise form. This is what 1 is in bitwise form. This is 4. Wait, no, this is 4. Yeah, okay. It's screwing up the 4 somehow. It's saying it's only 2 when it should have 4. Because bitwise and of 2 and 3 is 4. Yes, like yz and is equal to. Okay, xz or actually never made an appearance. I'll just comment that out. Min xy or. What the fuck? Why do we have 4 different values? Oh yeah, it is 4 different values. Because we know that the bitwise and 4 plus 2 plus 1, right? Yeah, because then xy or has to be equal to. Yeah, xy or and both of these have a 4 in them. It's just 4 plus 1 and 4 plus 2. Like even in here as well. It just depends on whether the b x, y, and 0, 0, 4. Yeah, so why is this not working then? That should definitely be working. D 8 times a plus 4 times b plus c plus d. Oh, mask. Okay, I'm stupid. I'm officially just stupid. 7, 6, 0, 0, 4, 7, 5, 6. Oh shoot, yeah. I'll include it. Screw it. Yeah, it's like 7, 7, 4. Yeah, 7, 6. It should be, what is it? 0, 0, 4, 7, 5, 6. 1, 2. It's still 1, 2, 4. Even though the mask is equal to 1, 7, or equal to 1 left of the bit. Yeah. Wait. Why is that happening? Wait, if mask is equal to 1 left at 2, else if mask is equal to this, else if at this, else if at this. Okay, 0, 0, 4, 7, 5, 6. Mask is equal to 3. Yeah, it's always equal to 3. Yeah. Okay. Plus bit. Okay. 0, 0, 4, 7, 5, 6. Huh? 2. Wait, it's literally adding this bit. What? It literally got that bit. Already at 2, or left if equal, or this value. 2 to the power 2 is 4. What? How is that possible? Wait. How is this happening? 1, 1, 3, 1, 2, 3. Else if mask is equal to 7. Okay, what if I do this? Like, what's happening then? 0, 0, 4, 7, 5, 6. Wait. Oh my god. I hate myself. I hate myself. I hate myself. Oh my god, I hate myself. I hate myself. I hate myself. I hate myself. Let me just confirm that the first 3 numbers are okay. 0, 0, 4, 7, 5, 6. There we go. Okay, well, that was stupid. That was nothing short of stupid. Okay, we got D. Very slowly, but at least we got it. Okay, time for E, I guess. Oh, that was so dumb. The minimum number of balancing operations or -1 if it is impossible. Wait, so we choose 2 subsegments, or subber. Wait, hold on. The items array A positions here get incremented by 1, and these get incremented by 1. So we can only increase values. It's like for some subsegment, it's like we increase this, increase this, increase this, increase this. So I guess it's dependent on for a subsegment. The only thing we care about are like the delta values, right? So can we remodel this in a way such that we only need 1 array? So in one operation, what happens is like these two, we want to make, in the end we want to make them equal, right? This gets increased by 1, this gets increased by, and so in other words, this gets closer to B or farther from B. In other words, the difference, like A minus B increases, but if we increase B, then A minus B decreases by 1. And we want to make it so that all differences are 0. So I think it's maybe after we transform this array, where like some positive and some negative numbers, the problem just turns into how many minimum number of operations we need, so that we choose some subsequence and we add 1 minus 1, add 1 minus 1, or say that it's impossible. I think that's how you can do it. Yes! When would be impossible? I mean, based on parity, I guess, because you have to choose an even number of indices, so the parity of the segment will always stay the same. So if parity is odd, then it's impossible. Is it always possible if it's even? I don't think so, because we could have something that's like 2 and then -2, and like, yeah, right? Yeah, we could have something that's like 2 and -2, and that would just be impossible. Because we could never, because we're basically, in one term we increase and like decrease, and then it's on the direction of that segment. So let's say, for example, our subsequence or subarray that we want to change was something, it was like 1, 3, 4 versus something like 2, 1, 2. The difference becomes -1, 2, and 2. I mean, okay, I'm going to change this to, let's just say 2, 0, and 2. That way it's -1, 3, and 2. And the parity is, still makes sense. You want to make it so that all of these values become 0. And on top of that, items in A position. Okay, so one thing that we know is that the sum between these segments never change. Like the overall sum of the segments. So this whole segment should add up to 0. Yeah, because even if we like increase something and it's like 4, 7, and this is like 6, 5, this difference over here is -1, difference over here is 1. And basically shifting it over here would like do that. So a necessary condition is the sum of all these differences have to be 0. After that, it then turns into a problem of, I wonder if it's literally just absolute value then. Wait, I'm gonna try that. I wanna just implement that and like see how it turns out. Well, okay, the thing is that we need to make sure that like the prefix sums, yeah, it's like the prefix sums. They like have to change in a certain way. So maybe you have to answer these queries offline. But if it's something like negative, because we have to do like -1 and then as it go like something along the lines of like positive, negative, and so on. Or like negative, or I guess positive, negative, positive. Like it doesn't, yeah, I'm gonna say positive, negative. So positive and then negative and then positive and negative and so on and on and on and on and on and on. Aga baga. Maybe that's how it works. I think that might be how it works. If we can do something like this, then we can take a value and just like edit it that way, probably. So okay, so we can do prefix sums to figure out whether the entire sum of this difference array is 0. Yeah, so we can figure out like the differences and see like when does it become 0, when does it not become 0. And then after that, we can then say like -1, we need like a pairing 1 over here. And that only happens when yeah, in any operation that we choose, it basically goes like 1, 0, 1, 0, 1, 0. Can we ever do -2, 1, 1? Yeah, we can do that. Yeah, of course, of course. -2, 1, 1. What if I do like -3? I mean, each value like gets increased with that, and if it's like this and it merges over like that, then it's based on the difference as well. Okay, I'm going to try this. Q and input 1 is equal to array at I is equal to this. And then based on, yeah, because any operation that we do, it will be like 1 minus, it's essentially like 1 minus 1, 1 minus 1, so in other words, if I do it for this segment, then A minus B will get increased by 1. And then increase 1, decrease 1, etc. P sums at I minus 1. Okay, so we get our prefix sum for this, and then after we get our prefix sum, we can then, the first thing we can query is to make sure the sum of the segment is equal to 0. Then after that, we need to make sure that there's no point in which these decreases become impossible to handle. So in other words, all the positives, or not all the positives, but like all of these, I guess, influences that we have to do. As like -1 and 1, we can basically pick any subsequence, any even subsequence, and just do +1, -1, +1, -1. It's just the caveat is that if it's like 2 and then -2, we can't ever do that because it's like +1, -1. Like this logic just doesn't work. So in order to circumvent this, we would need something that's like the sum of all these numbers. In other words, if we have a negative number in here, I mean, it's basically just a bracket sequence, right? It's like a weighted bracket sequence, I guess. And it's never possible if it's like on and off, if like it ever dips below 0. Let's try that. How do I handle that part though? I think I can just like answer the queries offline, then update using a segment tree. How would I update? It's like prefix sums, right? So, yeah. Do I want to use fast scanner for this? I'll just use fast scanner. It's a decent amount of input. And it shouldn't be too hard to replace everything. So we do this, and then we need to answer these queries offline, right? So it's just how does this part work then? We do like for like a lazy segment tree, we like we need to do range updates. So that we need to do it's like lazy seg tree range updates, and then like max or min query, something like that. And it could be longs. So how much memory do we have? I mean, it's probably fine, right? it's not fine, then that's just sad, but wait, let me think. Long. Yeah, these have to be longs. Long. Long, 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 long. Private long. Return combine. Combine is long. I mean, it's, we want to query the minimum. Yeah, it's a min query. We want to return like min query, and then null is, let's just say it's equal to, yeah, let's say it's equal to 0. So we only care when the min is less than 0. And then everything else looks the same. Yeah. Yeah, so lazy, seg tree, seg tree. Seg tree dot update I to I with p sums at I. Oh right, we have to change this to long. A long delta. Okay. Oh, right, I need to also get this, and then we do for n I is equal to 0, I is less than q, I is plus left is equal to queries add new query left right so after we added this, or like we processed these queries, right? Do this, and then we have our seg tree set up. We also have prefix sums. So for query q and queries, and L is equal to q dot left, and R is equal to q dot right. So if so long total is equal to p sums of R. If L is greater than 0, total minus equal to p sums of minus 1. If total does not equal to 0, then then it's queries at q.id is equal to -1 else, or not queries, res. Otherwise, if we need to, yeah, these queries are already sorted, so it's like int pointer is equal to 0. So while pointer is less than L, then seg tree.update. What do we want to update them as? Yeah, it's like this element just gets dropped. So it's just minus that. So it's just pointer. Yeah, just from pointer to yeah, from pointer to n or something. Pointer to n minus 1 because it's inclusive. Um, you want to update it by -1 times array at pointer. Sanctuary.query L2R. If at any point it's we add 1 and -1. So you want to start it off as negative. We never want the prefix sums to be greater than. Oh, so maybe it is max. Yeah, I think it's actually max then. If sanctuary.query ln_r is greater than 0, then it's impossible. Otherwise, it's or res at q and I is equal to like this. Otherwise, the minimum number of operations we need is, if it's all -2s, then it's just a bunch of like increases. Okay, well, every increase has to be in here, and then can we involve every value like that? Like, in other words, can we always do something like, because if it's -1 and 1, like, or like -3 and then 2, for example, and then it's just like negative versus like -3, then -3, 2, then -3 and 4. Is it always possible to do this in 3 operations? Like 3 total operations? No, it's not. How would we do this then? Oh, this is maximum of like all absolute values, right? Because we can always decrease the largest, because when we decrease the largest one, we always want to like handle everything else. Yeah, and then this is just like a sparse table or something. Or just like range queries. Like static range queries, pretty much. It's n log n, but we can do O1 queries. Or we can just do regular segment tree like this. Okay, I'm gonna just make sure that this is returning -1 for the correct cases. It is. Okay, nice. So now I just need to do like that range query type of thingy. Maybe. We'll see. Let's see. We will see. Class segment tree. It's just math.max. Yeah, that's whatever. Segment tree RMQ to get the new segment tree from 0 to n-1. RMQ.update at I, absolute value at array at I. Yeah. Ego beagle. Fuck. Okay, wait, hold on. One, three. Okay, from the second segment from 1 to 7. Okay. There's 8 elements. We're checking a segment from 1 to 7. So in other words, it's -2, -1, 1, 0, -1, 1, 2. This, yes. Okay, so it is okay. Oh, but we can't use. We need at least 3. Yeah. How do I solve this problem? Yeah, this part isn't quite correct. -1, 1, -1, 1, -1, or if it's -2, or something like we can carry these positive numbers over here, but is it also bounded by just how many negative numbers there are? Not really, no. Not really. I don't think so, at least. If it's not bounded by that or this, -2, -1, 1, 0, -1, 2. How do we figure out the minimum number of moves we need? -2. Okay, this can carry over, this can carry over, that carries over as well. One operation you can -2, -1. like this, or no. It's not a parity argument because the indices can be any indices. Alright, well, we know that it's like we can only decrease a number if it has a corresponding increase after it. Or like we can only increase a number if we have to decrease a number later on. Then it's just like greedy. Like from here if we have to just say like these elements of numbers, if it's like a priority queue type of thing, where it's like -2, like we have -2, negative. Yeah, because we have to increase this by this, and then we have to decrease, increase, decrease. That's one move. Wait, so, yeah, it looks something like increase, decrease. Wait, no. Increase, decrease, increase, decrease. Yeah, it would have to be something like this. And then in here, it's just like, we would need increase this, decrease this. So then it's just like, now increase this. No, wait, hold on. That's not right. Increase, wait, increase, decrease, okay. Or wait, does that even matter? Hold on, increase, decrease. I know I want to increase this one. If I decrease this one, then I could just say like I increase, decrease. Wait, the sum is the same though, right? Wait, why is the sum not the same anymore? Wait, I increased this, then I decreased this. I increased this. And now this is a decrease. Wait, okay, this is this plus 1, this minus 1, this is the same. This plus 1. Okay, I'm stupid. This minus 1. Okay, that makes more sense. And then it's just like that. It's like number of sequences or something. It's like plus 1, -1, plus 1, -1. Yeah, like the minimum number of moves we need to get from here to here is is it just, no, it's not the sum of all the negative numbers. Because we can still like, oh, maybe it's like the number of negative numbers that happen plus wait, rmq.query, this is a lower bound. Okay, this is a lower bound in our answer, but it's not a good upper bound. An upper bound, maybe it's like -2. Increase. Yeah, it's like increase and then increase, decrease, increase, decrease, increase, decrease. Okay. It's like decompose bracket sequence into minimum of these. Decomposing. It's like decomposing a bracket sequence, kind of. Decomposing a regular bracket sequence. Yeah, it's just that we want to find the number of bracket sequences we could turn that into. I mean, I guess it's just greedy, right? I want to figure out the largest depth, maybe. What if I do this? And it's like, what would this be like? Nothing. Oh wait, because null equals, well, private long and null is equal to long.min value over 2. Oh wait, so turning the max. Did I screw up? Oh wait. Oh wait, because I did. Yeah, if the max is greater than this. Yeah, but I want the min. I want a minimum value. Oh, okay. So no RMQ, but yeah, that's fine. Instead of using the segment tree, we just need another lazy seg tree for this. Lazy seg tree min. Min, same thing over here, except over here is just min. Okay. No. Alright, okay. Yay, buddy. Okay. I'm pretty sure this is still a rating loss technically, but I'll take it. Alright, 19 minutes for F. Let's get it, boys. Two B's have been hacked. This one probably is TL. Yeah, mine was fast. In training, also being in sport matches. N teams participate in each match. Each team is characterized by strength AI. Each two teams I less than J play with each other exactly once. Teams win with this probability. What was A again? Oh, A was like parody bullshit. Yeah, there's 3 hacked on B now. Maybe I should just try hacking on B, because I'm not solving F in 17 minutes. Alright. Is my B okay? Let's make sure our B is okay though. Let me also see like whether it was wrong answer or because like this one's probably TLE, but that was TLE. Maybe, I don't know. Wow, I don't even know now. I mean, mine. This shouldn't TLE. It's n log n, but it's like a fairly good n log n because it's just inversion counting with phemic tree. That should be fairly quick. What are other problems? C, I feel like C had enough tests, and like it's also the type of problem where it's probably like okay, it's probably like hard enough to just get whatever. Yeah. D is probably okay, honestly. I don't really understand why they asked for the kth element though. You could just ask for all the elements and the problem basically stays the same. E 2-second time limit is probably okay. I think n was only 10 to the 5. Yeah, it's only 10 to the 5. It's not like 5 times 10 to the 5. So that should be okay. I wonder, I mean, I'm probably losing rating, right? Like, I'm either like gaining a tiny bit or losing a tiny bit. I'll just check. Oh, okay. Plus 13 predicted right now. That's actually pretty good. I'll take that. What are my other friends? I know Purple Grand Pop Off. Yeah, he did very well. That's also pretty good. Yeah. Pretty legit. I think if I don't FST, I probably will not. If I don't FST, I'll probably end up gaining rating. But, yeah. Standings. Room. Not that many people even solved this problem, honestly. Garbage maker. Alright. I just want to check like a time limits real quick, like the run times on them. Yeah, okay. Mango Lassi is really good. Okay. Do I want to lock A then? Okay, what is my A again? The parodies aren't the same, then it's not as possible. X is equal to 0, then it's just the initial state. Otherwise, you just use one move and then use two moves. You know what? I'll lock that. I'll lock A. I don't think I'll be able to hack A, but just in case if anyone is like doing anything stupid, I can take advantage of that. I mean, this, yeah, if this, otherwise this, otherwise this, yeah, same thing. Okay. If their difference is equal to 0, yep. If C is equal to D, then if it's equal to 0, otherwise, yep, that's fine. If A plus B mod 2, yeah, okay. If A is equal to B, then this, it's fine. Mod 2, if C is equal to D and not C, these values, the inputs have to be positive or non-zero, yeah, non-negative. If absolute, yeah, I feel like all of these were probably okay. If A plus B, wait, if A plus B is equal to 0, oh yeah, because they're this. Otherwise, if they're equal, then it's this. If this, then that. Okay. Yeah. Yeah, like all of these look fine. Like I have not seen anything wrong with these, and I highly doubt. Wait a minute. What is this? Okay, so difference is always positive. Difference is this, okay? While A does not equal to B. Wait, this works? Well, B minus A. Okay, so take a difference. We decrease B by the difference. We increase A by the difference. Oh, okay. I see. That actually works. He just did it in a very weird way. Yeah, okay, all these look correct. Do we move on to B? We're like trying to hack B, I guess. Honestly, I don't know if I want to. Because there's like a non-trivial chance that... Actually, it might be, to be honest. It should honestly be pretty safe. It's just... Oh... 0, start on 0, start on 1. Yeah. And then inversions. Inversions are probably okay. Do we just like stare at scoreboard and just see what happens, or what? Like, what do we do now? Let's see. Problem C. Problem D is probably okay. E is probably fine. C is this. Yeah, maybe we just chill for a bit. Oh, you know what? I'll lock B. I'll lock B. I'll look at it like really carefully one more time. So we get the zeros, we get the ones. Total is equal to number of ones. So if it's odd in this, yeah. Otherwise, if it's odd and then this, then we have to start on 0. Yeah, and it's like 5 and then 3. Then we have to start on 1. We start on 1. Yep. We get it zeros. And that's just like the value itself. And then we have to count how many inversions exist. Start at 0, and then over here we check both of them. And then res is equal to min inversions. And then start from 1 to start from 0. Okay, I'm gonna lock this. Alright, B is locked. Check it out. That looks so Cancer. Oh my god. Do I even want to like try that? Oh my, why does that look so annoying? Let me just look at other solutions. Okay. I mean, these just look relatively convoluted, but I can't really tell if it's like, I can't really tell anything's like blatantly wrong. If that makes any sense. I'll just type this one up. If it doesn't, like, if nothing happens, it's whatever. X56B hack. I don't need this. Nor do I need this. I just need to rename this as hack. And T is equal to 420. Int n is equal to int math.random times 15 plus 1. Int array is equal to new int at n. For int i is plus array I is equal to int math.random times 420. It literally does not matter. Okay, so my solution starts over here. Solve in an array. Return. All right. And then we do okay, N A. So long odd is equal to 0, even is equal to 0, ants 1 is equal to 0, ants 2 is equal to 0, and W is equal to 1. Oh wait, did he? Oh, he's doing it disindexed. Okay, whatever, that's fine. Wait, what's position at W++? Pose, oh, okay. I'm gonna A is equal to this. Int pose n plus 1, 1 this plus 5. 1 is equal to 0, this is also 1. Okay, if k mod 2, so int k is equal to a at I, so if k at I mod 2, if k mod 2 is equal to 1, then odd plus plus, and then a at I is equal to 1, otherwise even plus plus. A at I is equal to 2, position at W, this is equal to I. If absolute value at odd minus even is greater than 1, then we return -1. Okay? Otherwise, int num is equal to 2. For and I is equal to 1, I is strictly less than W, I plus plus. We do answer 1 plus equal to absolute value at position I minus num. And then num increases by 2, and then num is equal to 1, for and I is equal to 1, I less than W, I plus plus. Same thing, probably, and then just return, right? Or answer at 2, absolute value, position I minus num, and then num increases by 2. If odd is equal to even, then we return the min at answer at 1 and answer at 2. Else if odd is strictly greater than even, then we return answer at 1, otherwise we return answer at 2. Okay, like, his solution was the same as mine, and I have 30 seconds left. Alright, that's my contest. Alright, that wasn't too bad. I wish I had more time. I definitely spent, I just spent a little too long time on C, D, and E. So I may or may not have been able to solve F, but it's whatever. It happens. Oh, wait, is Max becoming red? That's Pog. Alright. Well, like I said, I don't really have time to do careful solutions today, but I can just quickly talk about what I did for each problem. And I think I'll just do that right now. Okay. So, let me just open up everything. Yeah, I'll just open up all my solutions. I'm gonna check something for few minutes, then I'll get started. Wow. What is your... Okay, segment tree. Yeah, that's what I did as well. Okay, I'll just talk about, yeah, we'll start talking about these problems, I guess. Problem A, basically the way it works is that you notice that no matter what operation you perform on like what choice of k, the parity of the two numbers will always stay the same. So, in other words, if like your current values of a and b, if A is even, then b has to be even, and likewise, if a is odd, b has to be odd, before every operation as well as after every operation, like at any time. So if your target values don't have the same parity, then it's never possible to get those target values. So it's -1. Otherwise, what you can do is, obviously, you just do a little bit, of casework. If x and y are the same value, then you can use one move to just increase both numbers to the same number, to the target values, or if they're both already 0, then you don't have to do anything at all. Otherwise, if x and y, your target numbers, aren't the same value, then what you can do is, because we know that they have the same parity, their difference has to be same parity. So you can use one of those operations to essentially create this difference between like a and b, and then use a second operation to shift everything up into like correct value. So yeah, that's pretty much how problem A works. Problem B, I thought problem B is very standard. It's pretty much just like, you only consider like at most 2 different cases, and if n is odd, then there's really only one case you have to consider. So pretty much what you can do is this like property where you consider choosing 2 neighboring items and swapping them, this is exactly what an inversion is. And when it's asking for you to minimize the number of operations, you can instead think of a problem as, how can we minimize the total number of inversions to some goal state? So we can do inversion counting using something like a Fenwick tree, or in this case, because it's only 0s and 1s, you could actually do an O of n with a little bit of careful logic, but I just did Fenwick tree because that's the first thing that came to mind. Yeah, it doesn't really matter what you use, but what matters is just like, what matters more in this problem is what a valid state looks like. Because when they say that any two adjacent numbers at the end cannot have the same parity, what this means is that it basically forms like a one-dimensional like checkerboard pattern. It would have to be like either odd, even, odd, even, like etc. Or it would have to be like even, odd, and so on. And so those are really only two possible cases that you have to consider. So what you can do is you can just take every, or not every, well, yeah, you can just like count how many odd numbers are in this initial input, and then you can just figure out if is it possible to make this arrangement, and if it is, count how many inversions it takes to get to this arrangement. So yeah, that's basically how I did problem B. Problem C, this is kind of a weird problem, not super interesting, but I can pull it up. So problem C is like, you want to basically count how many regular like bracket sequences exist in like one big sequence. And the caveat is that the bracket sequence itself can have a ton of characters, but we can characterize these like opening and closing brackets as trunks. And there's only at most 1,000 of these trunks. So the way that we can do it is, well, the first thing you notice that because n is only 1,000, it makes sense to kind of like do an n squared type of procedure. And you can think of it as like you iterate on to like some like set of blocks, right? So if we have like an opening block and then a closing block and then an opening block and then a closing block, what that means is the first block that you choose has to be an opening bracket like type of block, and then the last block has to be a closing like bracket sequence, right? And everything else in the middle is already included. Like no matter what, you always include it. And you want to just figure out how many like choices, or like how many choices of like a substring, or not substring, can we take like for these like header blocks, like the first opening bracket block and the last closing bracket block. So the way you can handle this is, what you need to do is you need for this like middle blocks, in other words all the blocks that we consider like that are already inside the middle, all of those characters have to be included. And on top of that, we care about two things about the characters in the middle, like the middle blocks. We care about the total delta, and what I mean by delta is if you assign an opening bracket to 1 and a closing bracket to -1, the delta of a bracket sequence is just a sum of all of those like numbers. It's basically just like a subarray sum. And then the min is just the minimum, the smallest value that any prefix of this block will ever become. And the reason why we also need to consider the minimum a prefix ever becomes is if we don't have a value like that, there's no way we can distinguish between bracket sequences like this and this. Like, because the deltas over here, this delta is equal to 0 and this delta is also equal to 0, but this is clearly not a correct bracket sequence, because the minimum this can get is -2, because you can just take these first two brackets and that's -2, and the biggest that this and the smallest that this ever gets is 0. And so a regular bracket sequence will only like work if the total sum is 0 and the minimum is 0. That's the only time it can be a regular bracket sequence. So you want to use this property to kind of like do a little bit of casework. I did binary search to kind of play around with bounds. I'm sure you don't need to do that, but that's just what worked for me. And yeah, one thing that's worth noting is for the left like opening brackets, there's a range of how many opening brackets you can pick to have a corresponding like regular bracket sequence available for that number, for like X number of left bracket sequences in the opening block. So that's basically what I'm using a binary search for. I'm just finding the minimum number of left parentheses I need and the maximum number of left parentheses that I can include. So yeah, I just count this for pretty much every single pair of like opening block and closing block. And because n is only 1,000, this runs in n squared time. I guess it technically runs in n squared log n time, but it's a very good constant factor because this is more like 500 iterations since we're only doing every other. It's like 500 squared, which is like already pretty good. So yeah, that's a really quick explanation on C. I want to go to D and then E, and then we'll be done. All right, problem D. This one was the hardest problem for me. Yeah, I'd say it's probably harder than D. I mean C. It's definitely harder than C. I would say it's maybe even harder than E, or maybe about the same difficulty. I don't know. Yeah. So the main observation for D is that it's very easy to determine, like, let's say we have like two numbers A and B. So if we have like two integers A and B, we don't know what A and we don't know what B is for now. But we know what A and B is, and we also know what A or B is, bitwise and bitwise or. Let's just go ahead and assume for now actually that we know what A is. If we know what values, like if I replace B with a question mark and we want to find what the question mark is, if we know what A and the variable is, and what A bitwise or that same variable is, we can find what that variable is. So, and we can do that by just looking at every bit, and there's a little bit of casework. And that's what this section is over here, basically. Yeah, so that's kind of one trick that you can do, that you can notice. And it's like if you have A and B, and A or B, and if you have A, you can determine B uniquely. But now the problem is that we don't actually know any of these elements, like for sure, when we start. So we need to find some way to do that. And the way we can do that is, note we can use I guess technically 5 queries, but you can use 6, it's fine, since like it's 2 times n, so it scales up like fine anyway. But you can use 6 queries to figure out what the first 3 elements equal to. And the way this works is A and B is, if we want to find like values A, B, and C, we have to check A and B. We want to have B and C. We also have A and C. We also have A or B. We also have B or C, and we also have A or C. And these are like 6 queries. And if you think about a case where n is equal to 3, and you can only make at most 6 queries, but these are all the possible queries that you can make. And so just like the fact that this is a problem statement, that the way the problem is given, you can just assume that this is enough information to uniquely determine the values of A, B, and C. And that's just a lot of, in that part, I used a good amount of casework. I'm sure there's a better way of doing it, but basically the way I did it is I just looked at I looked at the values of A and B. So I'll like put these in parentheses, the important values. I used A and B, B and C, as well as A or B, and B or C. And these 4 quantities are actually enough to tell you which numbers have the which bit set, unless if there's only one case in which you have to be careful. In this case is where it's when if we're considering the certain bit that's set, these 4 values will be the same set of values if this bit is set in A and C but not B, or if the bit is set in only B. So if we have this scenario in which this happens, we need to include a 5th number over here. In this case, we can use A and C. And just to check, if A and C has this bit set, then we know that we're currently looking at this case, otherwise we're looking at this case. And so just like that, we can use, and we basically look at this for all 30 bits. And we only use these 6 queries in the first place. So yeah, this is how you can first use 6 queries to get first 3 numbers, and then use 2 queries to get rest. And then And then all you have to do at the end is just sort the array and then just find the kth largest number. The problem was kind of misleading in the sense that you actually could just find all the numbers and just output all the numbers, but they just had us output the kth largest, which I thought was kind of weird. But yeah. Okay, our B passed. Nice. Let's see. What else do we have? Oh, problem E. Right. So, how problem E works is that we basically just need to do like a few transformations. And I'll explain what these transformations are like in a second. But basically, what you can do is, you can think of it like this. All we care about is whether oh my god, I can't speak today. All we care about is whether a number in array A is equal to a number in array B. We don't actually care what A is equal to. All we care is that it's equal to B. So one way we can reword this condition is if we were to subtract AI by BI, we want this difference to be equal to 0. And so this kind of implies like this first step in which we know if we can take, if it's possible to make array at A equal to array at B, then we can just reword this condition to, if we get the difference array, where the difference array is like this new array C, where C at I is equal to A at I minus B at I, then we can reword a condition to, we want to perform operations such that some subarray of array C is all zeros. So that's like one like major transformation you have to perform. So that's basically what I'm doing over here. And so after that, you then realize that any operation you do, you have as many increases as decreases. And what this means is that every time you do an operation, the sum of the current subarray that you're checking, the sum of that subarray will never change. So in other words, if the sum was 0 before an operation, it's still going to be 0 after an operation. Because for every +1, you have a -1. Like +1, -1, +1, -1, +1, -1. No matter how many times you do that, it's all going to add up to 0. So we know that after every operation, since the sum stays the same, and our goal is to get all zeros, if the sum of a subarray is not 0 to begin with, then it's never possible to make all these numbers 0. So that's one condition that's like one condition in which it's not possible to transform like a subarray to all zeros. And that's what I'm doing over here. This tot is just equal to I'm just using prefix sums to calculate the subarray sum of like AI minus BI. So let's assume now that the sum of the subarray is equal to 0. If it's equal to 0, we actually have one more condition to check on whether it's possible or not. And the reason why is this. The way that we define these operations is we always have to have, like if we define like C at I, like if we define like this as like A at I minus B at I, what this means is that we can then take, we always want to take like +1 then -1, because the first operation, the first index, we always want to add it to a value of A, and the next index we always want to add it to a value of B. In other words, we first add by 1 and then we subtract by 1. And so it's always going to be +1 -1 +1 -1. If we have an array that looks like, for example, 1 and -1, if this is what the subarray, if this is the current subarray we're checking, this is not possible to transform. And the reason why this is not possible is because there's only one possible operation you can do, and that's always starting with +1 then -1. And so even if you do an operation, you're going to end up with 2 and -2. And there's no way to actually like decrease this value, if that makes sense. I mean, this is like the most specific case, but we can generalize this in a minute. So this is one thing that we have to be careful about. So now the question is, how can we generalize this condition, and how can we check it quickly? Well, this is now we can think about we can actually think about it in terms of bracket sequences, which is kind of interesting because it doesn't look like a bracket sequence problem, but you can actually think of it that way, and it'll help you solve it. So I just FST'd C. Oh my god, I just FST'd. Oh my fucking god. Oh my god. That's so annoying. What the hell? That's so annoying. Oh my god. What is this? What could this even FST on? It's probably an off by one type of thing. Whatever. Can't win these days, huh? Okay, whatever. What was I talking about for problem E? Right, for problem E, basically what you can do is you can just, like, if we think of like these +1s and -1 values, we can assign this like opening bracket as a +1, closing bracket as a -1, and we basically want to decompose this subarray into the minimum number of like these type of bracket sequences. And so in other words, it's always possible to do this. Obviously the sum needs to be 0, but also you need to make sure that at any point in the subarray, the prefix sum of the subarray never becomes positive. Yes, never becomes positive, at least in my case. It might be different in your implementation, but that's just how I implemented it. Aside from that, you can actually use that. You can actually like check that using a lazy segment tree. You can just like use range updates to shift this prefix sum into like the correct subarray, like left endpoint, and then you can just query like whether like there's a prefix that exceeds 0. And if there is, then the answer is -1. Otherwise, the minimum number of these sequences that you can decompose your subarray into is just equal to like the minimum number times -1. And the reason why is because I guess I didn't prove this I didn't prove this formally, but the intuition behind it is every negative number in the subarray can correspond to an opening bracket, and you can only assign that value if like on a prefix sum, if you consider like a prefix of like some subsequence, some like combination of these things. That's hard to describe. I don't really have a proof for that. It's probably better if you look at the editorial for a more careful proof of how that works. But yeah, that's my contest. I was going to gain rating, then I FST'd. I don't know how I FST'd. That's so annoying, but like, whatever. I think I should still keep orange. I think even with that FST, I'm still keeping orange, which is okay, I guess. But God, I've FST'd so many times recently. Like, if you look at my contest history, I FST'd a problem, bro. Wait, in the past 4 div 1s, I've FST'd in 3 of them. Wait, that's so stupid. What? Wait, that's so dumb. Okay, whatever. Alright, I hope you didn't FST like I did. Jesus Christ.